we'll transition from those concepts into the world of probability, you know, because we touched on the basic stuff, but you know, it wouldn't be much of a course if we only limited ourselves to flipping coins and rolling dice, you know. So we want to be able to make it as tangible as possible, right? So this is all part and parcel of that. I'm going to get rid of these stars because, again, I don't want people thinking this is any more important or less important than other things. So we have the union and we have the intersection, right? So again, the U is the union. That means, or. The upside down U, and this is just kind of like a little recap from last week, or last class, I should say. This guy here is equivalent really to, so it's the same as that symbol, which means and. Also known as intersection. So AKA, also known as intersection. And I kind of think of it, I sort of think of it that way, like the intersection, the way you would normally think of it, like the intersection on a road. I mentioned this last time, where you have two roads that are crossing one another. The intersection, the box, where you don't block the box. That box is the part of both roads that are common to the other, right? So road A and road B are the same at that intersection, right? So it kind of jives nicely with what we're talking about here, right? So when I say the intersection of A and not B, well, the first thing I would want to know is what is A, right? And so that's where a nice diagram comes into play. So that's what A is. Anything inside that circle is part of A, part of set A. Not B would be anything outside of circle B. So what I would be looking to do is kind of like invert the shading that I would do if I were shading B. You know, instead of shading inside of circle B, I would shade outside of circle B. All right. So it's just my app doesn't allow for that in the same cool way that it allows for me to shade inward. It doesn't allow me to shade outward. So I'm just kind of stuck with that, but it is what it is, you know. So what I would do is I would just start shading everything outside of B. I always get my orientation related to the shading a little wonky. I kind of feel obligated to fix it a little bit because I don't like the way this looks now. A little consistency. Still stuck with that little weirdness on the other end, but you could see that there's a part of this diagram that's double shaded. I'll make it a little bit more obvious. The part that's inside circle A, give it like a double shading aspect to it. That region is the part that is A and not B, all right? So it's consistent with being all of A that is also the part that is not in B, all right? So it's really strange, but getting the visual is going to help us to really kind of develop a plan when it comes to determining probabilities. Now, numbers 3 and 4 are probably the most important examples of this idea because you see one of them is the negation of A union B. So that's A or B, right? So let's take a look at that one. And the other one is the individual negations and the intersection. So let's take a look and see how these relate to one another. So first off, I'm just gonna consider. All right. So part of the challenge here is considering what you're dealing with. So I'm gonna just consider the inside part of the parentheses here and say, what am I looking for here? This is the symbol or, A or B. So A or B. All right. So if any part of A or any part of B is true, then the whole sentence is true. All right. So this is telling me that I'm working with any part of circle A, any part of circle B, even the overlap. All right. So instead of marking up this diagram, what I'm going to do is I'm going to recreate the diagram. Poorly. Oh, you know what? I don't want the shading. I can't get rid of it now. Oh, that's one of them. Good enough. So I recreated the diagram. Now I'm just going to kind of pull it off on the side. Make sure it doesn't go off the grid too. Yeah, I'll put it over here. We'll even throw in A and B. All right. So all I'm doing now is I'm just focusing on what A or B looks like. So A or B would be the shading inside of A, inside of B, including the overlap between the two. Let's kind of bring it all together in the middle. Kind of, all right? So what I want is not that, all right? So this is an example of what I don't want. I want the exact opposite of that. That's what a complement is telling me, all right? This is saying the opposite. All right, so here I shaded inside both of the circles. Okay, so I'm going to do the exact opposite of that and I'll have my answer. So I'm inverting it. I remember when I was growing up, you know, Windows was first being invented. I mean, not invented, but you know what I mean. And you know, I just always loved technology. So I wanted technology to work in like magical ways, like it did in the movies. But it never did because I grew up in the 80s and 90s. So you got what you got. But one thing I did get was Microsoft Paint, which really hasn't changed a lot in the last 30 years. You know, it's got some add-on features, but its basic programming is pretty much the same. One thing that it will do is it'll do an inversion. So if you have, you know, if you have shading inside a figure and you want to shade it the other way, you want to invert the shading, you know, like you have like you know, those, oh, the image of the stick figure of the guy scratching his head. What are they called? Not emoticons or emojis. People put them in their documents all the time. I just can't remember what they're called. Well, stick figures, like really like dark, shadowy figures. You can invert it, and the background becomes black, and the figure itself becomes white, or vice versa. You know, so that's all that's happening here. You know, so you're just inverting what you had is going to change to what you need. You know, it's going to be the exact opposite. All right. So how does that translate to number 4? Well, here I'm saying I need the opposite of A and the opposite of B. All right. So that's kind of a little bit of a trickier animal. But what we can do is kind of take on a similar approach to what we just did. You know, draw another diagram where we just focus on not A. All right. So that's what I'll do. I kind of regret shading this one in. You know what? I can just steal it and just erase it. All right. So let me get rid of all the shading in here. All right. So I want not A. All right. Well, let me do this a bit at a time here. Let me get rid of the B. Just for now. We'll bring it back in a sec. I'm just going to kind of chuck it off on the side. I'll create a new rectangle, I'll put the B in there. Just kind of disregarding it for a second. If I want just the not A, all I'm doing is I'm shading in this figure everywhere except for A. All right, that's not too bad. Not too bad at all. So then the not B, just kind of pop that down there. That'd be this guy. So I got not A, and this one would be not B. Not B is the same idea. I'm just shading everywhere except for the B. So then the big question would be, what happens if you put the two together? All right, I want not A and not B. So I want the overlap between these two sets. All right, so I want all of the not A and I want all of the not B, but then, you know, those are already separate. I already got those. Now I want to see what happens if they intersect with one another. If they intersect with one another. I was worried I was saying that wrong. So what I would do, overlay one of them on top of the other. Yeah, it gets a little messy, but that's the idea. All right. Now, you could see here that some parts of the graph are single shaded and some parts of the graph are double shaded. I'm only concerned with the parts of the graph that are double shaded. All right. So you could see here, inside circle A, I have just red shading. Inside circle B, I have just green shading. The intersection of A and B, I have no shading whatsoever. Right? So that wouldn't be in my solution set at all. I'm looking for the ones, the area that satisfies both. So that would be the part that's double shaded, red and green. Right? So, you know, I could pull it back apart. But the idea is to be able to say, well, what would happen if I put it all together? So again, I did it separately. I'm just kind of, I'll reduce the size so it looks a little bit nicer in the notes. Make it a little bit smaller. So we have that. And then when we put it together, that's where all the magic happens. So it's like, I guess I could make a GIF out of this, but I don't want to. I'm not a GIF guy. All right, so that's what we end up with. So then the question would be, okay, well, what does that translate to in a nice, crisp, clean diagram? Just shade your diagram only where the merging of the two graphs have the double shading. All right, so then you get the idea here. If you compare 3 and 4, that's why I said these are the most powerful examples. Oh, God dang. Pause. Look down for like a second, possibly 5 minutes. The important piece here is that when you look at numbers 3 and 4, you see that you have two different expressions that lead to the same shading, the same diagram. All right, which is super important. What it tells me is that we have a logical relationship between not A union B. That's going to be the same. It's going to be logically equivalent. That we do that. I mean, not to throw even more notation at you. This means logically equivalent, not A and not B. All right, so I'll just make a little note here so you have it. This means logically equivalent.
Does it always hold true that if you negate the contents within a parentheses, if you negate a statement, that the and will switch to an or and vice versa?
Yeah, but it only works between ands and ors.
Yeah, only between ands and ors. So if I have an or, it'll switch to an and then if I have an and, it'll switch to an or, and then the left and right side will both also negate or unnegate.
Exactamundo.
Cool, thanks.
And so that's an important relationship because now it tells me that depending on how complicated the probabilities are to find, like if I have a probability question where it's like, well, it's really hard to figure out not A and not B, but it's not hard at all to figure out not parentheses A union B, then I know that I can swap out one for the other. Right? That's the big takeaway on this. And like we're still kind of discussing it in a vacuum here, where it's like I haven't given you any problems where this would be applicable yet. But when it happens, you'll be like, oh, so it's either half an hour worth of work or 30 seconds worth of work. Oh, gotcha. That's why that rule is important. All right. So you don't know it till you see it, but when you see it, you can't unsee it. I just took like 5 cliches and just shoehorned them together into one like mega cliche. It's one of my strengths. So on the next page, talk about sample size. All right, so we've actually kind of addressed a lot of this, but it is the formal discussion related to it. All right, so sample size considerations really talk about getting at how many items are in a sample space without actually having to list out all the items in that sample space. All right, because when we're talking about probabilities, we're talking about, you can simplify it to part divided by whole. You could also think of it as number of outcomes that you want divided by number of total possible outcomes. All right, and you could also think of it. I mean, if you really want to stretch it a little bit, you can get into the like if you're talking about trials in a real life context, the number of attempts, like free throw attempts, how many did you make? Historically, how many have you made? Like I throughout my career, I'm an NBA professional. I'm such a wonderful basketball player. I've taken 10,000 free throws, which would be an absurdly large amount, but let's say that, for example, it is. And from those 10,000 free throws, I made 5,000 of them. So I'm historically a 50% shooter. I can project outward from there. But you don't always want to get to a point where you actually have to determine the total number of values in the set by counting them up. Sometimes, like if you can use a relationship, a mathematical relationship, well, not sometimes, all the time, if you can use a mathematical relationship, you should, right? So that's what these two examples are really getting at. They're very simple cases, but they're the building blocks of more complicated cases. Let me check the, we're gonna have to watch that at some point. Those Geico commercials are I mean, historically, they're just like the best. Good, clean family fun. Although I do love the Dikembe Mutombo one. That's probably one of my favorites. I'll just add it to the list. Flipping a coin. One flip yields two outcomes. Oh, look at this. It's like I had planned this. I have a little chart here. This is a stretch, but I'll take it. And I actually encourage people submitting these as typos too. See how the numbers are not in the middle of each column? 1, 2, 3, 4, and then N. They're not centered in each individual cell. I'd like them whenever I have a data table, I'd like the contents to be centered. So I don't remember to do that. So if somebody wants to submit that for typo bonus, I'll take that. That'll be great. So one flip leads to two outcomes because now I feel compelled to write it in the middle, and now it looks terrible. Two flips lead to four outcomes. Three flips lead to eight outcomes. Now, when you look at the progression here, you see, okay, we're doubling, obviously. 2 becomes 4, becomes 8. So the next one would be 16. I think that's pretty clear. I'm going to kind of try to make it work here based off of the formatting. So this is really going to become, this is 2. This is 2 times 2 to give you the 4. 2 times 2 times 2 to give you the 8. And then this one is 2. Well, I don't want to write 2 over and over again. It's starting to get a little out of hand. So instead I'll write 2 to the 4th power. All right. So what we're seeing here is a relationship where we're constantly taking the number 2 and raising it to the power associated with the number of trials. All right. So that 2 was raised to the 2nd power to get us that second entry. So this is 2 to the 2nd. This one was 2 to the 1st. 2 to the 3rd. We already said 2 to the 4th, but I'll write it again anyway. If you follow that progression, it makes perfect sense. I already stole my own thunder. That should be a 4. This one should be 2 to the nth power. All right, so we got a little relationship out there. If you can discover that relationship, it saves you from having to do the work. Because if I said, right, what the hell was that? Something fell in my room here. It scared the crap out of me. Well, let me pause. So we got a relationship. We know that 2 to the nth power is going to give us the number of outcomes. So if I say that I want to flip a coin 30 times, I could say 2 times 2 times 2 times 2 times 2 times 2 times 2. I can't even say it more than like 5 or 6 times before I start getting tongue twisted. But I could say 2 to the 30th power, and that'll give me the denominator of my fraction. Now, you're halfway there. If you need to come up with a probability, you need a numerator and you need a denominator. You got the denominator. Now you just got to figure out what the numerator would be. Now, easier said than done, but half the battle's already won. Right? When it comes to dice, same deal. You roll a die, you could have 6 possible outcomes. You roll 2 dice, you could have 36 possible outcomes. 3 dice, 216 possible outcomes. 4 dice, oh, now we're looking at the same kind of a relationship. And you see the numbers are getting out of hand pretty quickly. This is 6 to the first, 6 to the second, 6 to the third. The next one, logically, overuse the term, would be 6 to the fourth. Not mistaken, it's 1296.
Professor, you have 6 to the second for the number 3, for the third one. It's supposed to be.
Oh, you know what? I actually have 6 to the third. It's just such a poor quality 3 that it looks like a 2. Thank you, I'll fix it. That's the problem with my my penmanship. It's non-existent. It's terrible. All right. So, but thank you for that. I appreciate it. 6 to the nth power is what we'd be looking for if I had some unknown number of trials. So if I had to roll a die 47 times, 6 to the 47th power. All right. So we get our results there. Now, we can generalize this because it seems like what we're doing is we're taking the number of outcomes for one trial, and we're raising that to a power that's equal to the number of trials. All right, so we could figure out the total number of elements in a sample space, items in a sample space, just based off of this relationship. Now, we're going to find as we move forward that probabilities are very specific to conditions, you know, so we use certain techniques only under certain circumstances. So it is possible that we could come across a situation where this technique won't work, but in a case called what we're going to call independent events, and that's because everybody calls it that. I don't know why I said it that way, but independent events, this technique will always work. But there's really no point in talking about it right now because I haven't told you what independent events mean. Right, so we'll get there in a few minutes, and then from there we can start to really kind of get the party started with probability. All right, now just a little reminder, little things that come up throughout the course, because people are always interested when it comes to probability specifically. The first unit, you know, the material kind of is what it is, where it's like you learn how to make a histogram. Once you learn how to make a histogram, you know how to make a histogram. You can do 30 practice problems, but you're either going to get it or not get it after the first 2 or 3 examples. You know, you don't need to do 30 examples in order to understand how to make a histogram. But probability questions, they're so varied and context-based that sometimes you could have 2 different seemingly different looking problems that deal with the same exact context. And so I think for probability, experience is the best teacher. So you see next to each of the little topics throughout the course, you see the little squiggly brackets with those numbers there. Those are sections in the OpenStax textbook, right? I haven't really talked about that too much because it hasn't really been relevant. It's just for probability. It's definitely relevant because you're gonna wanna get some practice with this stuff, right? So if you work your way through the practice sections related to those practice problems related to those sections, then it'll give you a good foundation and also good experience with the different types of questions I can ask you on an assessment, right? Because again, we can go over a problem where I say 3 cards are selected from a deck at random. What's the probability of this, that, or the other thing? But then on a test, I'll say that 3 people are selected at random from a room full of, like whatever, people wearing black shirts, blue shirts, and green shirts. At first it seems like completely different questions, but they'll actually end up being exactly the same, but you won't know that unless you have the experience going in. So little recommendation, again, OpenStax textbook is free. I have I operate under the motto, if it's free, it's for me. I don't like when people have to pay to learn, and that's just kind of a rule of thumb. And it's basically because I'm still paying for my education. It's been 20 years since I graduated college, and I'm still paying for it. So I'm trying to help you all not have to pay for it. But so basically when I'm saying you got to go to a textbook for extra practice, I really mean it, because it loathes me to say that. But fortunately, this is a free textbook. All right. So just something to keep in mind. Let me take a look at the chat. It's a great motto, right? So you have the addition rule. The addition rule is I call it the rule of OR. I don't think I'm the only one that calls it that, but it's a good way to think of it, right? A free Samsung TV, that's awesome. My wife's parents gave us a couple of TVs, but I kind of look at that as like, that's technically free for me, but it's not really free because, somebody that's close to us had to pay for it. But like a real legit free TV, that's some serious business. And Samsung's pretty good. I like the Samsung TVs. Nice sharp quality picture. I mean, the zombies that are getting like straight up murdered on my TV screen right now, you could see it with like HD quality, crystal clear. Zombieland, if anybody's wondering, that's what I have on tonight. Exactly. Yeah, I always have something going on in the background just because I always get kind of lonely looking at the screen, and I like to have a little bit of background visuals going on. Exactly. So yeah, the addition rule is talking about either or. All right, so I call it the rule of OR. That's kind of an oversimplification of what its true meaning is, but it gets the job done, at least to get us started with the concept. The method is used to, you can see the blurb there, to determine the probability in a single trial. The key thing is it's a single trial. All right, so that means, for example, so I'll write an example, 1 flip of a coin. One roll of a die. One whatever, one card selected. The key thing there is that it's one of something. Now, that one trial can lead to multiple events happening, though. That's where the Venn diagram part comes into play. All right, it looks like my screen froze again, so here we are. It's just one of those things. Oh yeah, I could totally put zombie kill questions on the next exam. I just gotta, you know what? That'll be a typo bonus question. Somebody's just gotta send me that. All right, let me stop the share, start it up again. So somebody just send me a remind message saying throw a zombie question on the next test, and I'll definitely do that. Fairly well versed in my my zombie lore. Yeah. So here you can see the Venn diagrams talking about union, but AUB. All right. So the or situation involving A and B. So set A and B. So what we're looking at, here's A, here's B. We're looking at anything that's A, anything that's B, including the overlap. All right. So this is all of A, all of B, and then in parentheses I say including overlap. All right. So, for something like flipping a coin, it's a little tricky to make it work with addition rule. But an example of it would be something like find the probability when you flip a coin of getting heads, a single coin of getting heads or tails. Right. So I'll throw that example in there. Why not, right? So I can actually just kind of like slide it down a little bit. So the probability of getting heads or tails. Well, that's going to account for everything, right? Our possibilities are when you flip a coin, you're either going to get heads or tails. That's 100% of the outcome. So this would be a probability of 1. Now, it doesn't necessarily have to be a binary situation. Maybe when I'm dealing with a roll of a die, I could say the probability of getting a 1 or a 3. So you would think about a 6-sided number cube, otherwise known as a die. I get a little diagram up here. I'm just going to take that and bring it on down. So in my 6-sided number cube, otherwise known as a die, I'd be looking for any instance. This would be my set A is 1, my set B is 3. Anything that's either a 1 or a 3 would be part of my solution. All right, so here's a 1, and here's a 3. I have 2 boxes that meet my requirements. There's 6 boxes overall, and so that could be one way of representing the answer. Another way would be to reduce it and call it 1 over 3, but there is no requirement of reducing fractions in this unit, right? When it comes to probability, oftentimes I'll even say that you're better off not reducing the fraction. I'll actively discourage you from reducing the fraction, right? So leave it like this. I won't even write the 1/3 because I don't want people to go back and think that it was a requirement, because things taken out of context, you kind of lose the true meaning. So like 2 weeks from now, you're studying for the next test and you look at it and say, oh, he made it 1/3. I bet that means we have to reduce. No, you don't have to reduce. Now, one card selected, that could mean a bunch of different things. Are we talking about a standard deck? Are we talking about like tarot cards? What are we dealing with here? So what I'll do is I'll just make a fictitious set of cards here. I got a black card, poor quality black card. Still poor quality black card. You see, that's the only thing that seems to be slowing me down instructionally, is my complete and utter inability to produce reasonable diagrams. And let me just get one more color in there. You know, I'll get 2 more colors in there. Let me get like a trick question. This was this, I'll explain the trick behind it in a second, but this was the source of a straight up meltdown by a student one time in a class about 15 years ago. And I don't mean to laugh, but because she was like not happy because she spent a lot of time trying to figure out this kind of problem. But this is basically what it was. It was find the probability of getting a red or a black card. All right. So you look at it and you say, okay, well, where are my reds? I got 1 red card here. I got 1 black card here. All right, so we're good to go there. That's a total of 2 cards. This is the part that caused the meltdown. The answer was 2/5. All right. The idea behind it was there was a 5th card. You know, the purple card was purple. The green card was green. The black card was black. The red card was red. There's a card right here. That was the white card.
Oh. The white card doesn't get a border.
What's that?
So the white card just
White card has a white border.
The white card has a white border, yeah. So it doesn't show up. You know, and so there's 5 cards there. That's what that gap represented. When I went over that problem in class, because this was before like Remind apps and Blackboard and stuff like that, the student had a meltdown, cursing, crying, everything. It was, I mean, I was up in the front of the room like, I don't know what to do. They didn't go over this in teacher school. You know, like I had absolutely no idea how to handle it. But in the end, I managed to calm her down a little bit. But she was like, I stayed up all night trying to figure out that problem. I'm like, yo, you just got to go to bed at some point. Like, I don't know what to tell you. Like, sometimes you're just not going to get it. Just wait for the next class. Like, that's what it is. But, like, that was a rough one. So I won't put that kind of question on the test. I'm not horrible. So how does the diagram relate to the examples on the right? Well, because that's the thing. If I'm selecting 1 card from the 5 cards available, the brain melts, nice. So how does the diagram relate to the examples on the right? So we have a set of cards. I'll box them all in. Each one of these, I'll just use a regular pen. These are my cards. All right, so I have a purple card. I have a white card, a black card, a red card, and a green card. If I'm selecting one of the cards at random, and I'm looking for the probability that it would be either red or black, what I would be doing is counting off any card that satisfies the criteria, you know, being red or being black. So those are the 2 that I put the check mark on. But the mysterious one, the secret one, again, the kind that I would never put on a test because that would just be awful. That would be this one here, the secret white card. Based off of that space that I left there, the white card with the white border that you couldn't see, that gives you a total of 5 cards to choose from. So you have 2 that meet the requirements of the question, and there are 5 cards available, all right? So we've combined both sets, the red and the black, to give us our total of 2. but then the denominator is the collection of all possible cards that are available. You know, so that's how bad probability can get. You know, I think probability is hard enough without me going out of my way to try to make it trickier. So you don't need to worry about those like trick questions on my end. It's the kind of thing where it's like you got to be careful because sometimes there's a little hidden ingredient in the probability question that you didn't really consider, and if you don't, you know, you could kind of go off the rails pretty quickly.
So, quick question: If is the addition rule, can you extend it? So, like, let's say you're dealing with a deck of 52 cards, and you want to find the probability of finding, 3 cards. So, is it A or B or C becomes 3 over 52, depending on?
Yeah, exactly. So you could expand it to like that or concept can be expanded to any number of different possibilities. So I could say I have 52 cards and I want to know what's the probability of getting a heart or a jack or a 2 or an ace or, you know, pick another one, you know, and your answer would be a collection of all of the unique cards that satisfy the criteria that you set up. Right? So it can get pretty hairy, you know, but fortunately we're in the introductory statistics course.
So I'm not going to be able to win at Vegas with this class because that's kind of why I'm here.
Oh no, you'll be able to win in Vegas because we're gonna do an activity in a couple of weeks where I'm gonna straight up teach you how to win in Vegas. So it's like we're not gonna do like advanced like master's degree thesis, doctoral thesis type probability, but we'll do enough to get you to the casino. You know,
Nice.
have some fun with it.
I want to learn.
Yeah, that's part of the fun. Learning and having fun at the same time. That's what I'm going for, especially around 9 o'clock at night on a Wednesday. We got to make it fun somehow, right?
Exactly.
Yeah, like the people from the movie 21. Exactly. Yeah, my game's roulette, so I can teach you a lot about that game, and I will. And you'll see, you know, a lot of the stuff that we're talking about in this lesson right here is going to translate to that. So it's pretty cool stuff. So what I will do, because page 25 is just an example of different practice problems. What I'll do is I'll put a star on these problems for you, meaning give these a shot on your own for next class. We'll go over them together, but give them a shot on your own first. Because it's like the old cognitive struggle thing, where if you try to duke it out with these problems first, you'll learn from the experience. I'll go over them with you, but I want you to have experienced the problems before I do that. All right. Some of them are a little trickier than others, but you know, like it. Basically, I'm trying to tell you, don't lose your mind if you don't get it, because we'll go over it together and I'll show you little tricks of the trade and stuff like that. But if you do get it, then you're ahead of the game, obviously, you know. So let me stop that recording. I'm going to take